and it's a pleasure to be speaking at this very exciting webinar today. My presentation will focus on the role of green hydrogen and specifically e-fuel and e-methanol, so green ammonia and green methanol as fuel. So first of all, I would like to step back a little bit and give kind of a background on why we're having this discussion at all. So particularly, I mean, it was already mentioned, it could be an energy vector to transport hydrogen across the globe, but it's also key for decarbonizing transport. And I know there is a kind of a big discussion on the different decarbonization options in the transport sector, also in India. So from a purely efficiency point of view, we see that for passenger transport, so ordinary cars, direct electrification is the most suitable way of decarbonizing, since using electricity directly is much more efficient than converting electricity first to hydrogen or even further to e-fuels. So here, direct electrification could be the most suitable way. But then when we talk about long distance transport, so long haul transport, the picture already becomes a bit more nuanced. So here both could be an option, direct electrification, but also synthetic fuels. And it really depends on the range, whereas for shorter distances, direct electrification could be the most suitable option. For longer distances, hydrogen, so fuel cells, or even synthetic fuels could be a viable option. Then next, when we talk about shipping, only for very short distances, electrification is perceived as a feasible option. And here really e-ammonia and e-methanol are the main decarbonization options. And especially in the recent 2 to 3 years, we see a lot of discussions on those two alternative low carbon fuels. And then lastly, in the aviation sector, also direct electrification is difficult. So here, e-kerosene, so synthetic kerosene based on hydrogen, is seen as a viable solution. But also, we've seen recent announcement by manufacturers of airplanes that hydrogen could be a viable option. So focusing on ammonia and methanol as fuel, giving a bit of background on ammonia. So ammonia is a colorless gas with a very distinct smell, so you can clearly smell ammonia. Natural gas is used to produce conventional ammonia today. So in the first step, natural gas is converted to hydrogen, and then in the next step, with the help of nitrogen, hydrogen is further converted to ammonia in a very carbon-intensive process. And today, the majority of ammonia is used for the production of fertilizer. However, in the future, ammonia could also be used as a fuel for maritime shipping, but also as a replacement, for example, of natural gas used in the industrial processes, and also as an energy vector. So shipping of hydrogen via the ammonia route and then cracking ammonia back to hydrogen, then to use hydrogen as a final energy carrier. Next, methanol. Methanol is a liquid, it's colorless, and it's also today produced mostly from fossil fuels, mostly natural gas. Also important to note that methanol is toxic, and it's today used as a chemical building block for basically hundreds of everyday products, including plastic, paints, but it's also used as a fuel and fuel additive. Again, future use cases could include as a fuel for maritime shipping, but also as an energy vector for transporting hydrogen. Next, I want to go over the production methods. So both for e-ammonia and e-methanol, hydrogen is the key ingredient. So you have to make sure that the hydrogen is produced in a sustainable way. So in the first production step, you need electricity, you need renewable electricity from solar, wind, or hydro. And then in the second step, you convert that electricity with the help of water through electrolysis to hydrogen, to green hydrogen, renewable hydrogen, and then you take that hydrogen in the ammonia route. You combine it basically with nitrogen that you get from an air separation unit, which uses electricity to again get in the end ammonia through ammonia synthesis. And methanol is a very different production route. So here you need, instead of nitrogen, you need CO2. And that is actually the most critical part in terms of the entire sustainability of methanol, because depending on where the CO2 come from, also depends, also kind of, sets up the whole sustainability of methanol. So there are different options to supply CO2. It could be from industrial appliances that emit CO2. You could capture that and then utilize it in the methanol production. You could use biogenic sources, which then would get you to a net zero product, or you can either use direct air capture, so directly capturing CO2 from the air. But the latter two methods, so using biogenic CO2 or CO2 from the atmosphere, are more costly than using CO2 from industrial processes, but only the last two, so biogenic CO2 and direct air capture, would get you to a fully sustainable product, so net zero methanol. So next up, I want to quickly talk about the advantages and disadvantages of e-ammonia and e-methanol. So starting with e-ammonia, so e-ammonia has no carbon emissions. It doesn't contain any carbon. So the chemical term is NH3. Ammonia becomes liquid at already minus 33 degrees Celsius, which is easier to produce and transport compared to hydrogen, where you need roughly about minus 240 degrees Celsius. Also, a big plus of ammonia is that infrastructure is already in place. So ammonia is being traded today at a very large scale. However, on the flip side, ammonia has a low energy density, so 2 to 3 times lower compared to conventional maritime fuels, which in turn means that you require larger tanks and larger storage facilities. Ammonia is also toxic and corrosive, and it has this very intense odor. Especially the toxicity is a concern. For example, in a discussion in Germany at the moment on importing ammonia is quite driven by this toxicity aspect, whether those terminals that could import ammonia can be located in densely populated areas such as Hamburg, or whether that is not actually feasible, since an accident could lead to significant harm. And then last but not least, also a flip side, a downside of ammonia, that it emits NOx, which is of course a harmful pollutant both to the environment but also to people. On the methanol side, again, similar to ammonia, the infrastructure and the engine technologies are already in place. A huge benefit is that methanol can be handled and transported under normal temperatures and pressures, so it's a liquid, and it's been used for decades as a basic chemical in many industries. Also, an upside is that it's quickly dissolves in water and biodegrades rapidly. So if there is a spill into the environment, it wouldn't be as bad as an oil spill, for example. On the flip side, it also has a low energy density, however, slightly higher than that of ammonia. It's also toxic and corrosive, and it comes at, especially if you want to produce it fully sustainable, so from either direct air capture or biogenic emissions, it comes at a very high cost. And then the last negative aspect, which I put in brackets, are the carbon emissions. However, if you use direct air capture or biogenic CO2, you then have net zero emissions. So you take carbon out of the air and then, or from biogenic sources, and then emit it at the end. But if you take it from, for example, fossil sources, then in the end you get to carbon emissions that, of course, then accelerate again climate change. So what is driving ammonia and methanol? First of all, and I want to focus here on the shipping aspect. So shipping accounts for 2 to 3% of world's GHG emissions. 80% of those emissions come from long-haul ships. And really, ammonia and methanol are seen as the key decarbonization option for shipping. Within the IMO, so the International Maritime Organization, they're currently discussing on whether to introduce a carbon levy on fuels, so at $100 per ton of CO2, that then would incentivize the switch to renewable fuels such as e-ammonia and e-methanol. On a European level, the European Commission plans to include shipping in the European emission trading system starting by mid-decade. And last but not least, the EU also proposed Refuel EU Maritime, so setting GHG intensity targets for fuels, which basically means that the fuels used in shipping need to decrease in GHG, so greenhouse gas intensity, over time, and then by 2050 have to be 75% less GHG intensive compared to 2020. And here the GHG intensity is looking at the full life cycle of the fuel, not just the emissions from the ship itself, so also from the production. And last but not least, I also want to highlight some recent developments with regards to e-ammonia and e-methanol. So there are developments, for example, in ammonia ships. So ammonia either used as a fuel, as a combustion fuel in an engine, but ammonia could also be used in a fuel cell. And here Fraunhofer is actively researching that, and a first vessel is expected to be produced already next year. Then we have green methanol. So here we have Maersk, which is one of the largest companies in that field, but also MAN, Hyundai are looking at producing large-scale vessels that run on methanol, and in particular MAN, so which is one of the largest producers of engines for those vessels, is looking at dual-use engines, so which can run both on conventional fuels, but also methanol. And here we would they expect to be on the market already in 2 years. And then just two other examples. So we have LOHC, so liquid organic hydrogen carrier shipping. That's a different technology where basically hydrogen is attached to other chemicals. And then last but not least, we have liquid hydrogen, both as a fuel, but also used as an energy vector to transport energy across the globe. And with that, I'm at the end of my presentation, and I would hand it back to Teresa. Thank you.
Thank you very much.